Well, greetings, mathletes, and welcome back. Today we're going to be talking about exponential functions, and this is a lecture that's going to be split into two parts. This first part is going to be focused more on how to use the calculator, which will be very brief, and how to graph these things. And I'm not talking about graphing them on the calculator. We're talking about graphing by hand, getting an intuitive feel for how these things look, what are the major points that we need to graph. It's a lot like graphing a parabola, where if you know certain features of the parabola, you can figure everything else out and get a graph. So we're going to be focusing on those features today, and then how to translate it, move it up and down, back and forth, things like that. Usual stuff with graphs. So without further ado, let's go ahead and get started here. There we go. What I want to do is just look at computing a few things on the calculator. So let's say, most of the time we're used to our exponents being rational numbers. At the very worst, it's a fraction or something like that. So let's go ahead and start there. So we'll start with something like, let's say 6 to the third. We'll start there. And then, which should come out to 216, I believe. And then let's try 6 to the square root of 3. And then something like 5 to the 4/7 power. So I want to plug each one of these into the calculator. And as long as we can do this, we should be good for anything we need to do in this section. So let's see here. We got to turn it on. So if we're going to do 6 to the third, we need to know where our exponent button is. So for the TI calculators, it's a little symbol that looks like this. You see it on your keyboard. Actually, it's the on the keyboard of your computer. Excuse me, I couldn't think straight. It's the second function over 6. So it's that same caret that you're looking at. The other button that you might see, sometimes it'll be X to the Y will be the button, or Y to the X. It'll look like one of those two also. But in this case, it's this caret. And if we want 6 to the third, we just go ahead and type in 6 to the third, and we get 216. Right? No problem. Now, if we want 6 to the square root of 3, that's a little bit different. So we have 6. We still need the to the. It is a very good idea whenever you have something that's in an expression and it's an exponent, put parentheses around that expression. So if we want a square root, let's see. Boy, I can't even read this screen. There it is. So it'd be second function over the square. And we want the square root of 3, so we'll go ahead and close that. That one closes the square root. That one closes the exponent. And so we end up with, now that's an irrational number that goes on forever. So your homework will tell you where to round it. I'm going to say 3 decimal places for now, just because that seems like fun. So it should be 22.27, and that we're going 3 decimal places, so that 3 rounds to a 4, right? So that's our approximation. And then the last one, and quite honestly, I'm not entirely convinced that we needed the parentheses on this one, but good rule of thumb for parentheses and exponents is if in doubt, put on parentheses. You're never going to make it wrong by putting on parentheses. You will make it wrong by leaving them off when you actually need them. Okay, so 5 to the 4/7. So let's see here. We got 5 to the, and especially since it's a fraction, if I don't put the parentheses around this 4/7, what'll happen is I'll get 5 to the 4th. It'll find that number and then divide that number by 7, because it's going to follow the order of operations otherwise. So we have to have the parentheses around the 4/7 so that the calculator knows it's a unit. There we go. And so we get 2.50848, blah, blah, blah. It keeps going. Again, I'm going to round it to 3 decimal places. So this would be 2.50, and let's see, it's 84, so it doesn't round up. So 508. All right, so as long as you can get through things like that on your calculator, you should be fine for the rest of this. So I'm going to go ahead and close that for the moment. And let's go ahead and do this. Go ahead and fill that back in and clear that off, and then we'll get started with the main stuff here. Okay, so when we're talking about exponential functions are functions that look like this. Now, I do want to point out, I'm doing this a little bit differently than your book. Your book is actually just looking at this to start with, but I find it's a little bit easier to do it, to explain it the way I'm going to explain it. And it is completely consistent with what your book says. Now, there's a couple of things about this. So, if I'm graphing an exponential function, there are certain things that happen. One, just like any other function, if I make x 0, what I get is the y-intercept, right? That's true for lines, it's true for parabolas, it's true for polynomials, it's true for rational expressions, it's true for exponentials. So if I plug in 0 here, right, f of 0, what I get is a times b to the 0, which is just a. So what that means is that this a is your y-intercept. Now, keep in mind, this is an unshifted graph. We haven't put any vertical translations or horizontal translations or anything like that in there. We're talking about the unshifted graph. When it's unshifted, I have a y-intercept at a, wherever a happens to be, right? Now, there's something else that happens here, and we'll see it when we look at our first example. But these things, because they're exponential, and there's no exponent that will make a positive number negative. What ends up happening here is this thing gets closer and closer and closer to the x-axis without hitting it. It's what's called an asymptotic behavior. We've looked at asymptotes already. Now, with those two things, the only other thing to decide. In fact, I'm going to draw this twice because there's two different basic graphs that we could be looking at. And there's two cases. Both of them have the same y-intercept. Both of them have the same asymptote. And the asymptote is at y equals 0. What's different is that one of them will approach the x-axis on the left and blow up to infinity on the right. And the other one does the reverse. Right? It blows up on the left. They're mirror images of each other. Right? Now, these two cases, you can tell them apart because this case over here on the left is when b is greater than 1, and the case on the right is when b is less than 1. That's not a 1. Let's try that again. B is less than 1. Right? Now, in the general form here, the one thing that has to be true is, or actually, I guess it's two statements. B has to be bigger than 0, and B is not equal to 1. I'm going to have a hard time if I can't tell the difference between 0 and 1. Right? B can't be negative, and if it can't be equal to 1. I mean, if you think about it, 1 to the x is a pretty boring function. It's just equal to 1 all the time. Right? So it's just a horizontal line. So that's part of the reason we throw that out. Now, with the negatives, why we can't have negatives, if I just look at this, right? If x equals 1, I get negative 1. If x equals 2, I get positive 1. But if x equals, say, 1/2, I get I. Right? So it becomes one of those things where every little division is going to be, it's going to bounce between positive, negative, imaginary and real, all this kind of stuff. So we just throw out all the negatives because they cause too many problems. Okay, so now that we've done that, now we've looked at some of these basics here. It's really just a matter of getting our hands dirty and starting to play with some of these things. So let's see how this plays out. Yeah, so let's say I want to graph f of x is equal to 3 times 2 to the x, right? Now, This is how I like to do it. Okay, so I looked to see if anything has been shifted. Since nothing's been shifted, I can go ahead and put in my asymptote and my y-intercept. So here's my asymptote at y equals 0 on the x-axis, right? And my y-intercept is going to be at 3. So it's right there at 3. Now keep in mind, again, this is because this graph is unshifted. Now I can look here at the 2, and 2 is bigger than 1, which means it swoops up to the right. Right? Now, if you need an additional point, right, one of the really nice places you can put in an additional point is just let x equal 1. And that'll give you an additional point you can play with. It'll actually tell you about this piece right here and tell you about how steep it gets and how fast. So if I let x equal 1, right, f of 1 is 3 times 2 to the first, which is 6. So at 1, this should be at 6, right? And so you can always drop that 1 in there to get an extra piece, just to get an idea of how steep it is, because sometimes you need to know how steep it is to tell what the graph is. Yeah, and if I look at another one here, let's say I take a function g of x, and g of x is equal to, let's say, negative 2 times 1/2 to the x, right? Okay, so let's take a look at what we have here. Now, you could be thinking, hey, that's a negative. That's going to flip the graph upside down. And you'd be thinking absolutely correctly. You can actually deduce that, though, from using it as a y-intercept, because this is an unshifted graph, which means that I have an asymptote on the x-axis, right? And that means whatever's right here is my y-intercept. Well, that means the y-intercept is at negative 2. It's right down here. Since it doesn't cross the x-axis, that gives me an idea of what it looks like, right? And since it gets closer to 0 on the this number is less than 1, which means it gets closer to 0 on the right rather than on the left. That means it goes, instead of being the one that goes up here like this, we get this guy, right? So we flipped it upside down at the same time. So if the number is bigger than 1, then it gets closer to 0 on the left, right? If the number is smaller than 1 like this, then it gets closer to 0 on the right. And you can use that to dice things out, right? Okay, so let's take a look at another one. This time let's add a little shift in there. Oh. There we go. All right, so let's say I have f of x is equal to 2 times 5/4 to the x plus 1. Okay, so now we have a shift involved here. Now, before the shift was involved, in fact, I'm going to do this with 2 different graphs so we can see without the shift and then adding the shift in there. Now, if I ignore this shift to start out with, right, that plus 1, I would have an asymptote here on the x-axis, right? My y-intercept would be here at 2, right? There's my 2. And 5/4 is bigger than 1, so that means it's closer to the x-axis on the left. So it's going to, well, we'll pretend this is a smooth line. So it's going to do something like this, right? But now we have to add 1 to it. Well, if we add 1 to every value, what it's going to do is it's going to shift everybody up exactly 1. We don't have to map out every single point. We just have to map out the main points. So the asymptote now, this guy, now shifts up 1 also. So this asymptote is now at 1. So this is y equals 1. and this was 2 units above the asymptote. So you're counting how many units above the asymptote it is, and you're just keeping that rigid. So now instead of at 2, this intercept is at 3, and it keeps its same shape. Right? So it should be something like that. So the whole thing just shifted up by 1. And so basically you add 1 to every value. Anything you've measured, the asymptote, the intercepts, all of them, just shift everybody up 1 and then graph it again and you're good to go. Right? So it's not too bad. But you do have to pay attention to details because there are, well, the devil's always in the details. Okay, so let's take a look at another one here. Okay, so for this one, let's suppose we have f of x is equal to 3 times, actually I don't need that parentheses there, 3 times 2 to the x plus 2. Okay, so we'll go ahead and take a look at a couple of these things here. So first of all, let's forget about the plus 2 and just look at what it would look like. Let's try that again. Look at what it would look like without the shift, and then we'll play with the shift. Okay, so without the plus 2 on there, the y-intercept would be at 3. I'd have an asymptote on the x-axis, like so. And 2 is bigger than 1, so that means it will go up to the right and down to the left. Right? So it should look something like that. Right? General ballpark anyhow. Now, plus 2. Now that is a transformation inside the function. That's kind of akin to taking, you have f of x is equal to 3 times 2 to the x, and this is taking f of x plus 2, right? And remember, when I do something like that, take an f of x plus 2 or an f of x minus 5 or whatever, it's a horizontal shift. So it's moving left and right. And it always moves the opposite direction of what you have. So this is actually shifting 2 to the left. Right? Something like that. So let's see here. And actually, let me do this. I'm going to move this down a little bit, like so, just so we get everybody in there. Okay, so if I want to shift this, I need to move 2 units to the left. So what I'm going to do is do exactly that. So if this point right here is moving 2 units to the left, right, it's still at 3, but it's over here now, right? So this swoop is actually going to be coming out of here. Now, the horizontal asymptote here, well, if you can just picture what happens to a horizontal line if you shift it left or right, it's still a horizontal line. So this doesn't change the asymptote at all. The asymptote is still on the x-axis. Right? So the one thing that would be helpful here, we know this is our point that used to hook to the y-axis. So it would be nice actually to know what the actual y-intercept is. This isn't always practical. Sometimes the number is just way too big because these functions grow quickly. But if it's a reasonable number, we can graph it and it will help us. So let's see here. If I want a y-intercept, it's always f of 0. So that makes it 3 times 2 to the 0 plus 2. So 3 times 2 squared, which is 12. So that is up there a ways. Right? But let's just say this is 12. We'll just agree to it. And so this guy, this is a horrible drawing. But you get the idea, right? It swoops up this way. And it goes through the x-axis, or excuse me, the y-axis at 12. And so really what's happened is it was right here, and it shifted over, right? It just slid over. It would probably be more useful if I actually drew them in the same shape, but you get the idea. It's just a matter of moving it over horizontally. Okay. Where do we go here? There it is. All right, so those were the main points that I wanted to hit for this. Um, some of the graphing is intuitive. If it really comes down to it, plug in points, right? If you just plug in a couple of points, you can have things to graph and you can connect to dots. The shapes of the graph are one of two shapes. It either swoops up to the right and gets closer to the x-axis on the left, or it swoops up to the left and gets closer to the x-axis on the right. It's just a matter of telling which one you have and then figuring out how it's been oriented around on the graph. So in any case, that wraps it up for this lesson. And until next time, keep your pencils and your wits sharp.